You are with Cape Talk.
Views and News with Clarence Ford.
At 9:38, we welcome Dr. Chris Smith, lecturer at the University of Cambridge, better known in these parts as the Naked Scientist. Great to have you, Chris.
Good morning, Clarence.
I must tell you, it's going to be, well, the jury's out, 32, maybe 39 degrees in Cape Town today.
I can see your 39 degrees and I can lower you to -5, which is what it is here right now. I've just taken my son to the station to get on his train to school and my car told me it was -5 degrees C. Beautiful, what? Absolutely beautiful this morning. Wonderful starscape because it was still dark, but very, very cold indeed.
There's 45 degrees discrepancy in the differences of temperature between where you are at and where we are at. I can't even imagine that.
But yeah, I got 2 pairs of socks on today because it's just bone-chillingly cold. But this is kind of normal. We've got lulled into a false sense of security for what the new normal in climate terms and winter temperature terms is. We've had warm winters relentlessly for years. And so when we occasionally get a glimpse into what it was like for real, like this is how it should be in these sorts of latitudes at these times of year, you kind of think, oh, it's got cold. But no, this is sort of what it is. And this is artificially warm, actually, here. We're warmer than we should be, in the sense that if you carry on along the same line of latitude, you will get from London to Moscow. And in Moscow, it's beyond -20. And in parts of Canada, of course, at equivalently high latitude, the same sorts of very, very low temperatures. So we're kept artificially warm because we have a phenomenon called the Gulf Stream, which is a patch or pool of warm water, a stream of warm water that arises from the Gulf down at where Florida is, and it's directed north across the Atlantic and goes past the west edge of Europe and then up the west coast of the UK, and it delivers huge amounts of energy to the North Sea, the English Channel. And this keeps the water around the UK much warmer than it should be. And this is blown onto the land by the prevailing wind, which means we're artificially warmer than we would normally be, which means we can exist at these high latitudes without having Moscow-type temperatures.
It's actually very difficult to understand Moscow and London being on the same latitude, but it is actually. Wow. But okay, so let's get to your questions. I see there's a couple in. What is bull dust and why is it so dangerous, Dr. Chris?
I don't know. And if anyone can help me, please let me know. I've not heard that phrase. I wonder if it's from a bull mill, because when you are grinding up ores to extract useful things or precious stones, precious metals and so on, you can put things into a ball mill. And a ball mill is when you bounce around big metal balls inside a rotating drum, which smashes up your ore and the stones and so on and helps to extract more of the precious stuff like gold from inside. But that's a ball mill. I don't think it's a bull mill, but it does produce a huge amount of dust. So I wonder if that's what it is, but I'm just speculating. If anyone does know and can help me, please help me out.
Okay, then we've got the voice note. Let's take a listen.
Morning. Dr. Chris, I'd like to know what causes our stomach to be upset and have diarrhea when we eat chili, like hot wings or something, any food that has high spice content or high chili content. What is it in chili that makes us have diarrhea when we have chili? Lucas.
Well, a couple of things to think about here. And one is that it could be the chili, but it could also be something else which is in the food, because if the food hasn't been stored properly, cooked properly, prepared properly, and the chili, strong flavours are being used to mask poor quality meat, which has been subject to all of the above, it could be that something else has grown in the meat. Listeria, for example, very, very common in some places, particularly as a friend of mine who did some microbiology experiments around Joburg found, very high fraction of the food outlets around Joburg were serving meat that had listeria in it. Other food poisoning organisms which can secrete toxins into meat, like Staphylococcus aureus, where meat's been poorly handled and poorly stored, you can end up with toxins secreted into the meat. And again, the chili is used to mask the fact that the meat is of poor quality. And when you eat it, it's not the chili upsetting you, it's some other passenger that's on the meat. But yes, some people do seem to have a sensitive constitution for the strong flavour in chili, which is the spicy ingredient, capsaicin. Most of the receptors for capsaicin are on the outside of your body, in your skin, your mouth and your bottom end. So you tend to notice things when they go in and when they first come out, but you're less sensitive to the effects as they go through. So I would say that the former point I made is the more likely explanation for why you sometimes get a bellyache with these sorts of things. But equally, some people are sensitive to these effects. You can activate the receptors through your guts if you have a strong enough dose of chili, and it causes an irritation. And the body interprets irritation in your gastrointestinal tract as something trying to poison you, so it tends to put things either into reverse, and up they come, or it smooths the path through and accelerates things so that they leave the body quickly. Either way, you try to remove from the body the irritant, which is what the ultimate goal is.
We have another voice note. Okay, let's go to the text notes in. Hi, Naked Scientist. Please explain, how does a boomerang work? Abdul wants to know.
Hi, Abdul. Well, a boomerang's effectively a wing, and as it curls through the air, it is driving air over the curved surface of the boomerang, and this is having the effect of generating some lift, which works in the same way as an aeroplane wing, which makes the boomerang fly. But because the boomerang is also turning and it's pulling air over the surface of the boomerang, the arrangement of the shape and the way it's been thrown, as it passes through the air, it means you get a torque or a force on the boomerang, which when you add all these forces together means it goes out and slowly describes an arc coming back to you. So there's several things going on. One is that it's got the capacity to generate some lift and fly through the air like a wing, which gives it the ability to fly stably and in a straight line, so you can throw it and hopefully get to a target with it. But then the other aspects of the way it's shaped and is turning generates forces that bring it back on the path it started out on.
Okay, somebody's weighing in on the bull dust. Of course, we know the nonsense or the rubbish that it could be referring to, that we sometimes speak. But I think in the instance, it was bull dust is a fine, soft, and powdery red aeolian dust that is common across Australia. So that's the bull dust with reference. And the next question is it's Len. Len is on the line. Let's go to the phones. Len, welcome. Go ahead for the Naked Scientist.
Morning, Clarence. Morning, Dr. Chris. Difficult question. In South Africa, our electricity supply is 220 volt, 50 hertz. In America, it's 110 volt, 60 hertz. My problem is, what is the difference, or what's the effect of the difference between 50 hertz and 60 hertz? What is the difference? What is that effect on the usage of electricity?
Hi, Len. Well, we use, ever since Tesla really introduced us to how we can distribute power most effectively, and I should say more accurately, energy more effectively, we use alternating current. And what that means is that you have a sine wave. You're basically generating the electricity with a moving rotor which spins through a magnetic field, and it's set up to turn through that magnetic field, so the current that flows in the wire changes direction 50 times a second. That's why it's 50 hertz in South Africa or the UK. If you change the speed of your rotor so it's a bit faster, you'll get 60 hertz. It's changing backwards and forwards 60 times per second. Now, it doesn't actually matter that it's 50 or 60 hertz, it's just the industry standard. And we stick to a standard for various reasons, including that we can tell how underload the grid is by what that frequency is. But the reason we use alternating current is it's very easy to transform. When you transmit electricity, you do so at very high voltage. And you do that because if you increase the voltage, you can decrease the current that you have to transmit, and the power losses in a transmission line are directly proportional not to the current, but to the square of the current. P equals I squared R. So the resistance of the wire stays the same, but the current square is what dictates how much energy you lose in the transmission. So if we can get the current right down, we can save huge amounts of energy. So if you double the current, if you halve the current, you quarter the losses because of the resistance. So we use alternating current to step up the voltage to a transmission voltage, and then we step it down again close to people's homes, and then step it down again into people's homes. That's easy to do with alternating current. People build transformers that can do that for us, but you need alternating current to do it. But really, whether you go at 50 or 60 hertz, it's not going to make a huge amount of difference. But some bits of equipment do rely on that frequency in order to, or knowing what that frequency is, to make various measurements about grid performance and about how much load there is and so on. So as long as you use that and stick to it, it shouldn't be a problem. Most bits of equipment will work happily if you get the voltage right in the two different jurisdictions. The difference is cameras, and you might have noticed if you buy a webcam which is marketed internationally, you can set the camera so that it will have a compensation for either 50 or 60 hertz mains. And this is because the lights, when they're flickering because of the mains, are flickering 50 or 60 times a second. And this means the camera would see that, but it can compensate for those effects if it knows what the frequency of the mains is. So you choose either 50 or 60 and you can remove those effects so your webcam doesn't look all flickery.
Then we have a question in from Scott, and Scott's question is, why is there a hexagon at the top of planet Saturn?
I didn't know there was a hexagon there, but there might be a configuration of the gases on the surface of Saturn that make it look like there's a hexagon there. Jupiter has a giant red spot, for example. We think that's a big storm because these gas giants are absolutely enormous balls of chiefly hydrogen with a few other bits and pieces added too. So if we take Jupiter, for example, this has a diameter of 10 times the Earth and a mass of about 1,000 times the Earth, mostly all gas. But it's not static. It's not staying in one place. The gas is moving around. And this leads to various storm systems and patterns on these planets, and Saturn is almost certainly no different. And the result is that because of the interaction of gravity, the moving gas, the rotation of the planet, other gravitational influences, you will pull things into various patterns, and the energy coming in from the sun then drives the movement or convection of these gases as well. And you do end up with patterning. And as I say, Jupiter's got the giant red spot. I'm not familiar with Saturn's hexagon, but I would say probably the phenomenon is quite similar to what's going on Jupiter. But that's my speculation, and if anyone knows better, do let me know.
Okay, I think we're going to stay in the stars for a while longer. Before we ask the next question, you're welcome, of course. Drop your question via WhatsApp on 072-567-1567. You can also call and interact directly with the Naked Scientist, 021-446-0567. If the universe is in motion and expanding, why do stars like Orion's belt remain the same distance from us after so much time?
Well, this is not actually true. And if we were to go back many millions of years, the skyscape would change. The reason that the stars don't appear to move to our eyes, and remember that not all stars remain in one place, what we call stars, in fact, some of the stars do move around, and that's because they're planets. They're much closer to us. And the Greeks actually gave them the name planets from their word planetes, which meant wanderers, because when they looked at the night sky, they saw that there appeared to be two populations of stars, some that stayed in one place relative to each other and some that moved around a lot. We now know the reason they moved around a lot is because they're close to us and they're planets. The stars that don't appear to move are really stars, like our sun, but they're a long, long, long way away, and over those vast distances they don't appear relative to each other and to us to be moving. But if you were to wait a really long time, because the universe is in motion, that's quite right, the stars in the Milky Way are all in motion. They're going around a central black hole in the Milky Way, and they're also bobbing up and down in and out of the plane, because the Milky Way is a spiral galaxy. There's something like 200 billion stars in there, and it's rotating around that central black hole. But the stars don't just go round in a circle on a flat plane. They also exhibit what's called proper motion. They bob up and down like the horses on a merry-go-round go up and down as they go round on the carousel. And the stars are doing the same. So over long periods of time, as in millions to hundreds of millions of year timescales, the stars do move relative to each other. It's just we're looking in a very narrow slice of time because we're only here for a blink of an eye. Our timescales are very short compared to the timescales over which the universe operates.
And I think we have one more question. When they drill for oil or gas and they find a potential deposit, how do they measure what the yield could be, seeing that it is stored in porous rock and not a hollowed cavern structure? Secondly, I guess there is not much oxygen in these deposits. So if magma was to break into these deposits, then it will not cause an explosion. That's a long one for you, Dr. Chris.
Well, first of all, how do we know where the fields are and how extensive they are? Well, the reason there's oil and gas in the ground at all is because there's geological configurations and conformations down there which make it possible to trap the material. It takes millions of years to cook and stew organic material which fell to a seafloor usually and landed in a hole and was then covered up. It takes millions of years under high temperature and pressure to cook that into oil. The conditions are really only stable for that to happen and for it to be then trapped and kept there in certain places on Earth where there aren't fault lines and where there isn't likely to be the emergence of magma, which could do what's happening in Iceland at the moment and trigger volcanoes and things like that. So really, where you find oil and gas, you don't find volcanoes, for example. So that's the answer to that bit of the question. In terms of the extent of those reserves, because we understand the geology that leads to them being there, geologists have become very good at spotting the right places on Earth to look, and also then using various measurements to look at what the structure of the underlying geology is, to work out what the extent of a potential yield or holding could be. One way they do that is by sending vibrations into the Earth. You detonate explosions close to the Earth's surface, and in the same way that a ship can detect a submarine by sending sound waves through the water that bounce back and echo, you can send vibrations into the Earth from explosions and listen to the echoes that come back, and these will reveal where there are interfaces between different rock types and different strata. And these, we know what the patterns are, or the configurations are, that lead to the right sort of geological structures to trap oil and gas. And once you've got the extent of those sorts of things, you can then do test drillings. And once you've got test drillings, they can tell you a lot more about the structures that are down there and the likely yield were you to tap into it. And then once you bring all those things together, you then have to bite the bullet and decide if you're going to try and exploit that. And further test drillings are made. This is very expensive to do, obviously, and it's higher risk, but then you begin to draw up what's down there, and you can do further analysis to look at the quality of it, the composition of it, and also how much of it there's likely to be.
Barris, I think we've got time for your question. If you can squeeze it in quickly, we'll appreciate it.
Morning. Hi. Now, I'm just curious now. I came back from leave, and when I was on holiday, the views that I was seeing with my eyes was like, wow. But when I look at the photographs, they're not the same. Why does a digital camera or cell phone capture the same as what I'm seeing?
Because your brain, Barris, is doing huge amounts of extra processing to what goes in through your eyes. Each eye has about 1 million nerve fibres in its optic nerve connecting that information to the brain, but we're only paying attention to a tiny part of the visual scene at any one moment in time, and our brain is filling in the gaps in terms of what's being presented to our consciousness. And this is why when you look at people doing experiments such as they focus your attention on something and then in the background there's something that you hadn't noticed until your attention is drawn to it going on. And this is how our attention works. Now, a camera doesn't have that discrimination. A camera does not spotlight certain things of the visual scene and add emotion and add colour enhancement and draw your attention to things. A camera just literally captures some information and stores it. And the key to being a good photographer, I'm not one, but I know some people that are, is to know how to set the scene up so that you anticipate where people's brains are going to want to look and what they're going to want to see, so that your brain can then easily do those jobs on top. And a bad photograph has too many distractions, not enough of the focus and the focal point in the right sort of composition in the right way, so that people then can't recreate the scene in their mind's eye as though they were there. A good photograph enables you to transport yourself to that location as though you were seeing it for yourself.
And then, Katlego, I've got to squeeze this in, maybe just a yes or no answer. Do mosquitoes prefer a certain blood type?
Well, they certainly like certain people, and that's because those people smell good to a mosquito. They produce lots of CO2, and that includes pregnant women, but there are also people in the population who, for genetic reasons, produce a cocktail of volatile chemicals from the skin, which to a mosquito smells much more attractive. There are also people who produce more chemicals that mosquitoes find a deterrent, so they tend to get bitten less. And some of those smells may associate with certain blood types, but chiefly it's what you smell like to a mosquito that dictates whether or not you're more or less likely to be bitten.
We managed to squeeze it in, Katlego. That answers your question. Mom, in this particular instance, doesn't get bitten. The rest of the family does. But that's it. Thank you, Dr. Chris Smith, the Naked Scientist, every Friday after 9:30. Nearly time for news at 10.